Okay, we're recording. So, last time we were considering this question here of, what happens to a surface if you do the following to its equation? And the big strategy here is if you understand how, algebraic adjustments cause geometric adjustments, then you can take, for example, an equation whose surface you already understand. You can do an easy whatever that is, an easy replacement in this case, replacing all the z's with two z's, and you can conclude then exactly what happens to the surface. And in particular, what we argued last time was that this kind of vertically smushes the surface, kind of squishes it in the vertical direction. So, the idea, sort of the general pattern that we're noticing is that whatever you do to the variable in the equation, here I sort of replaced all the z's with two z's. I introduced a factor of 2 in the equation connected to the z. In some sense, kind of the opposite is what happens to the surface, right? And that's because loosely speaking, and let's not get super rigorous about this, because of that extra factor of 2, you need these z coordinates to be half as big for the arithmetic to still work kind of like it did before. Okay, so that's the big moral, and a couple of examples of how to apply this. If you want to know what does this equation look like, then I'm going to say, okay, well that looks a lot like this equation which describes this surface that I already understand, and I know exactly what happened. What do I have to do to the variables in this equation to turn this equation into that equation? And well, in particular, everywhere I see an x, I need to replace that with x over a, right? And then likewise, everywhere I see a y, I got to replace that with y over b, and likewise, everywhere I see a z, I need to replace that with z over c. So I need to do these 3 adjustments to the equation. And what does that mean about the surface? Well, all of these sort of exact opposite things are going to happen, right? So in particular, here we kind of, you might want to say, divided by a on the x variable. So that's going to then geometrically do the opposite and stretch by a factor of a in the x direction. And then likewise, we're going to stretch by a factor of b in the y direction, and we're going to stretch by a factor of c in the z direction. Okay, so nice punchline then. Because we understand how algebraic adjustments cause geometric adjustments, I know now what this equation represents, and it represents an ellipsoid. By the way, a little terminology to make sure you know this is ellipsoid is because this is kind of a 3D version of an ellipse, if you will. Okay. All right. Analogously, a couple more examples. We already know that this is a paraboloid. And sometimes it's called a circular paraboloid because the horizontal cross sections are all circles. Right? Well, when you do these adjustments here, where you replace x with x over a and y with y over b, you're going to stretch it out accordingly. And so this is also kind of a paraboloid, but instead of having circular cross sections, it's been stretched out in the x and y directions, so it's now what we call an elliptical paraboloid. It's got elliptical cross sections instead of circular cross sections. Okay. And etc. So here's a hyperboloid of 2 sheets. We talked about that last time, and rotation argument and all of that. So this hyperboloid of 2 sheets, notice that if you do the adjustments that you need to do here, replace x with x over a, etc., then, well, that's just going to sort of stretch it out as well. And so this is going to be, again, hopefully no surprise, an elliptical hyperboloid of 2 sheets. Okay. Now, one little fine detail I do want to talk about. A lot of students make a mistake here in thinking about what we did to the x's in particular to turn that into that. And a lot of students mistakenly think that we're replacing x with x over a squared. And that's not right. Right, so very importantly, we're just replacing x with x over a. And let me stretch out the algebra just a little bit here to show you what's going on here. X is something that's squared, and then minus y squared minus z squared equals 1. This is, if you will, kind of what we have to start off with. And this is where x went. So what is it that I would have to put in that place in order to make the result, let's see here, in order to make this result here, x squared over a squared. And the key point, obviously, is that whatever I put in here, all of it gets squared. Right? So whatever you replace x with, all of that is going to get squared. Right? So if what you have is x squared over a squared, think of that ideally better as x over a quantity squared. And that'll make it easier to see that it's that the thing that needs to go in this place where x had been is x over a, not x over a squared. So be careful with that little algebraic pitfall. Okay, so moving on now to 2.3. So we're going to talk about derivatives. There's actually a bunch to say about derivatives, no surprise, I hope. The rest of chapter 2 pretty much is about derivatives and things you could do with derivatives and different ways to think about derivatives, etc. So in particular, notice I say plural here, derivatives, and it's because there are multiple types of derivatives. This doesn't really happen in single variable calculus. In single variable calculus, there's the derivative, pretty much, end of story. I guess you could talk about the second derivative, right? But that's just a derivative of a derivative. It's really kind of the same thing applied multiple times. We're going to find multiple very different, fundamentally different kinds of derivatives. And what they all have in common, and the reason we can call them all derivatives, we can use the same name even though they're different things, is because they have this common feature. They always relate input changes to output changes. And if you think back to single variable calculus, Calc 1, I think you'll notice that in some sense that's a point of view you can take on what a single variable derivative is. Okay. All right. So our multiple different kinds of derivatives are going to relate the input changes to the output changes in different ways. But they all relate input changes to output changes. Okay, I'm going to start off with partial derivatives. There's some good reasons for doing this. Mathematically good reasons, pedagogically good reasons. For one thing, they're really easy to compute. We're going to find that momentarily. And I have a nice, convenient, let's get one in the win column, right? This is an argument for that, for sure. They're also what I'm going to call kind of familiar. They're easily relatable to single variable derivatives. So it's not just going to be that they're easy to compute, they're going to be easier to understand. You're going to kind of notice the analogy. Again, give me 15 minutes and we'll be there. Highly analogous to single variable derivatives, so that makes them easy. We're also kind of have our hand forced here a little bit. The book here starts with partial derivatives, and that doesn't exactly force me to follow their pattern, but it's a strong incentive to do that, and I think the advantages of going a different way are outweighed by the advantages of staying in the same order that the book is. It gets a little squirrely if you go out of order. But I want to give you a warning, though, and that is just because we're starting with these does not mean that this is sort of the fundamental cornerstone point of view that you should have on derivatives. In fact, I don't think they are. These are not... When you leave this course in May, right, and if someone were to ask you... Fundamentally, you got 10 words. Fundamentally, what is a derivative of a multivariable function? I hope that those 10 words will not include the phrase partial derivatives. So anyway, what you should say instead is something we'll talk about possibly later today, probably Friday. Okay, so anyway, just again, word of warning, don't hang your hat on partial derivatives as being fundamentally what this course is about. Okay, here's how you compute them, though. Again, it's a convenient place to start. Gives us some easy wins. What we're going to do is we're going to take our multivariable function, right? We've got a bunch of input variables, and we're going to make a choice to hold all of the variables constant except for one of them. Let's arbitrarily say the ith input variable. So all the rest of the variables we hold constant, but this one variable we choose to leave as a variable. And if you think about it, if you have a function that depends on a bunch of variables, except most of those variables aren't allowed to change, I mean, are they really variables if they don't change? Aren't they kind of constants now, right? So you don't really have n variables anymore. Now you have one variable and a bunch of constants. So, in fact, then, the result of this is that you're now effectively looking at a single variable function. And having chosen to make this, this seemingly odd choice of I'm going to just choose to hold a bunch of my variables constant. Now you have a single variable function. You can just take the derivative. I mean, calc 1, just the regular it's a function of one variable. Just take the regular old single variable derivative of that function. So this is what a partial derivative is. Now, why we are interested in such a thing, what is it good for? What does it look like? What other ideas that I'm going to be interested in does it connect to? Oh, that's a long conversation to follow. But in terms of how to compute them, that's all there is to it. Okay. Now, a little bit of notation. Here's the sort of first notation I want to show you for partial derivatives. Do notice that this symbol here is not the lowercase letter d. Very importantly, not a d. You can't write a d there. That's it's a problem. You really can't. You can't do that. So heads up, you cannot put a d there in its place. And it's also not a lowercase Greek letter delta. So just, FYI. So I know that this is a little bit silly seeming, but I think it's a healthy exercise to just go ahead and take 30 seconds and kind of practice making that symbol because, if you haven't made it before, if it's not in your handwriting repertoire, right, it's going to feel a little weird writing it, and you want it to be natural. To feel natural as you write it. So again, it seems a little silly, but it's a good investment of 30 seconds. Okay, and with all of that noted, let's actually compute one now. Now, I'm going to start off with what looks like a hard question. Right? We're going to take a partial derivative with respect to y of, oh my gosh, look at this monster. It's got 3 factors. One of them is a composition with a product, including an exponential, the product rule and the chain rule and the, oh gosh, which way does cotangent go? There's all sorts of things that looks kind of scary about this. This could take half a page to kind of write it all out. So it seems. But very importantly, remember, when we're taking a partial derivative with respect to y is a variable. Therefore, y squared, that's a function we're going to have to deal with. But x is a constant, and that means that e to the x is a constant. And it means that x squared is a constant. Don't forget z, also a constant. So e to the z is a constant. So this product is a constant. So that cotangent is just a great big ugly constant. Right? So most of what we have here in this seemingly ugly function is actually a great big constant. So really, this is just constant times y squared. And when you take a partial derivative of with respect to y of y squared, you just get 2y. And the constant comes along for the ride as constants do. Right? Same constant, just repeats. And then, just aesthetics, I tend to like to take that factor of 2 and move it out to the front. Just, I don't know, it's just math etiquette, maybe. So anyway, that's all there is to that. Everybody see what happened there? Okay. All right. It's very important when you're taking partial derivatives to keep careful track of which variable is actually my variable, and then by process of elimination, that all of the other variables you should, for the purposes of that calculation, you should view them as being constants. Okay, so here, let's see another example, a couple of examples here. And here we're taking a partial with respect to x. Okay, fine. Well, if I'm taking a partial with respect to x, that means y is a constant. That means y squared is a constant. So what I've got here is a function to the power of a constant. It looks like a function to the power of a function. But as far as this partial derivative is concerned, it isn't. It's a function to the power of a constant. And of course, we follow the usual rules there. Whatever that constant is, it gets kicked out to the front, and then you subtract 1 in the exponent. And then, of course, don't forget the chain rule. You have to take the derivative of the inside and multiply that times your answer. Everybody remember all that? Chain rule stuff? Okay, so this at a glance looks like a logarithmic differentiation problem. It's not. It's just a power rule problem. Okay, likewise here we're taking a z partial. That means that z is our variable, and that means that all of this is just a constant. This is basically saying what's the derivative of k to the power of z. And you may recall, this is another old single variable calculus rule, that when you have k to the power of z, you just get k to the power of z times the natural log of whatever that k is. So, again, single variable calculus. Looks harder than it actually is. Okay, so with all this in mind, I nominate partial derivatives as being the easiest derivatives to compute, because they're just like single variable derivatives, except you get to just pretend that large chunks of your function are just constants. So even easier than single variable derivatives from a certain point of view. Does that make sense to everybody? All right. Okay. All right, now, reminder, I made up a seemingly very arbitrary rule, unmotivated. I wrote down a notation and see that my unmotivated manufactured rule is easy to compute with, but it remains that I have no reason yet to believe that this is actually good for anything, right? Does this, what does it mean? What does it look like geometrically? Does this relate to anything like in the physical world or geometric, or what does it look like, right? So that's a big question that we need to address next. What are the geometric interpretations? And I'm going to remind you that the answer to this question depends on what kind of a picture you're looking at, right? So we talked about this last time, or I don't know, the time before, and graphs are a completely different construction from level sets. Calculus is going to look really, really different on level sets and really, really different on graphs. So if you want to know what does calculus look like, what are the geometric interpretations of calculus constructions, what does a partial derivative look like? Well, very importantly, are we looking at a graph? Are we looking at a level set? We're going to get very different answers depending on which of these constructions we're looking at. So we're going to start here by looking at graphs. Everything that follows applies only if you're looking at the graph of the function you're taking a partial of. And we're going to have a completely different analysis for level sets and et cetera, et cetera. Okay, so graphs. Notice I'm looking at a graph here, right? Value of the function, 2 inputs, 1 output. Value of the function is set equal to a new variable z. I want to consider what the y partial of this is, just to get the ball rolling. Partial with respect to y. And specifically, though, partial with respect to y, when I'm at this point a comma b in the domain, keep in mind our domain is kind of the xy plane down here, and so we're looking at this point a comma b. So at that point, what is the y partial of this function, and more to the point, what does it look like on this picture? Everybody see the question we're asking here? Okay. All right. Well, here's the good news. The process of computing a partial derivative. Remember, there's 2 steps. First, set all the other variables constant. Second, take a single variable derivative. Both of those steps have existing geometric interpretations. So I don't have to, in some sense, reinvent the wheel. I just have to put the puzzle pieces together on what we already know. So let's walk through that and see how that works out. So step one, remember, keep in mind we're taking a y partial. Set all the other variables equal to constants. There is only one other variable, it's x. So we're going to set x equal to a constant. Reminder, we are doing this at this point, a comma b, where x is equal to a. So if I'm going to set x equal to a constant, and if it's already a, then I have to pretty much set x equal to a specifically. And that means effectively I'm writing down this plane, x equals a. Is that cool? Notice, now this is a little bit awkward. I don't know. Anyway, it's easy to get this confused, I'll say that. It's x that we're setting equal to a constant, and as a result, notice our cross-section plane is pointing in the y direction. So it's easy to get that backwards, and Anyway, heads up. Be careful about that. Okay. Right. Now, so fine. What does that give us? Well, we had, the graph we were looking at was a surface, and now, though, by fixing that value of x, that cross-section is just a curve. And what can I say about this curve? I'm going to point out that curve, again, it's where z is equal to f of x comma y, except, wait a second, x is now a constant. X is now fixed. X is now a, and it's not allowed to change for the purposes of our conversation. So this purple curve that I've got here really is just, let's see here, I'm taking a partial with respect to y here using blue. So what I've got here is z now just as a function of y. So I've got height as a function of y. Height as a function of a single variable is how you make the graph of that single variable function. Right? So, for the purposes of partial derivatives, we fix all the other variables. We interpret our multivariable function then as a single variable function. This cross-section is the graph. Right here, the graph of our new single variable function. Okay. Next question. Next step. Having fixed x, interpreting our single variable function like that, what do you do when you take the derivative with respect to y? What does it geometrically mean when you take the derivative with respect to y? Well, derivative, single variable function, derivative is the slope of the tangent line. Right? That's our Calc 1 interpretation of derivative. So, there's our answer. This slope, the slope of that tangent line to the curve that was the cross section of our original surface is what the partial derivative is. And so I have that summarized in this statement right here. If you want to take a partial with respect to y, as you might sort of hope, it's the slope of the tangent line, kind of like it is in single variable calculus. Derivatives are slopes of tangent lines. Quick clarification. That is tangent line to the graph. This only works if you're talking about a graph. And specifically, because you're taking a partial with respect to y, we want the tangent line, we want the cross section in the y direction. So, there you go. This is what that y partial is. Geometrically, and this is the picture of it. Everybody okay with that? Okay, now I have an exercise for y'all, a suggested exercise, if you're so inclined. I do think this is a healthy exercise. First, make sure you're comfortable with this argument that we just made that gets us down to here. Take all the time you need to digest that and understand each sort of step along the way and how did I draw the picture, etc. Right? Get fully comfortable with it. And when you're pretty sure you understand all of that, confirm for yourself. think through all of the analogous reasoning, right? That the x partial is the slope of the tangent line to the graph in the x direction. I mean, it's exactly what you would expect it to be. But how do you draw the picture? What are we holding constant? What does that mean about the cross section I'm taking? And blah, 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 right? And think it all through, draw the pictures, make sure you can produce on your own this argument about x partials. And again, this is the answer that you'll get. Make sure that this is the answer that you get when you do that argument. Okay, again, I think that's a very healthy exercise, something to think through. And of course, if you have questions, come on by office hours. Happy to help you through if you get stuck on something, or if you somehow keep getting the wrong answer and you're not sure where your reasoning's going wrong. Come to office hours and we'll straighten it out. Okay. Now that was all about graphs. Now I want to think about partial derivatives in a couple of different contexts now. So remember, not everything in this course is going to be graphs. Much of it, we can't even draw a graph. So for example, you take this situation right here, 3 inputs, 1 output. I can't draw the graph. That's 4-dimensional. Forget about it. Right? I can't. Whatever I think I know about derivatives in the context of graphs does not help me here. Right? Okay, so here's what we're going to do instead. I'm going to try to develop some ideas about, in this literal picture, we have the domain, and the function takes points out of there and plops them down here into the target. Right? In this literal picture, what would a partial derivative with respect to y, let's say, look like? Or what things that I can see in this picture would the y partial kind of relate, and in what way? Okay, so here we go. We're taking the partial with respect to y. That means that x and z are fixed. And of course, they're fixed at these values, a and c. So we're going to be staying on that line described by when z is equal to c and x is equal to a. Those are our other two variables. For the partial derivative, they're not allowed to change. That confines me to that gray line there. Everybody good? Okay, so now if I'm on that gray line, of course, I can talk about, well, what would happen if I moved by some amount, dy, some differential amount, dy, in that direction. And well, what would happen is the value of the function would change by some amount, some what we call differential amount, df. Right? You got an input change, there's going to be a corresponding output change. And if you think about it, this is now really the picture of a single variable function. Again, we've made this observation before. When you're doing a partial derivative, you're interpreting the function as effectively a single variable function, where there's your kind of input space and here's your output space, and the function kind of takes me from the one to the other. And we already know how to interpret single variable functions derivatives in terms of input changes and output changes. The input change relates to the output change in that the derivative is what you multiply by the input change to get the output change. So this right here, old fact from single variable calculus. And of course, in this case, we're effectively reinterpreting this as new information about partial derivatives. If you're looking in this literal picture, where the domain is over there and the target is over here, I don't really have a picture of the y partial that I can point to, but it's a relationship between these things that I can. It's a relationship between the input change dy and the output change df. Is that cool? Everybody's happy? All right. Okay, so yeah, different geometric interpretation. Notice it's not a slope, right? Very importantly, not in any sense a slope. Okay, level sets. Again, very importantly, not a graph. Now, let me show you the blunder that a lot of students make. This is very common. Again, training from high school, we just sort of effectively or by default allowed to, whatever picture we see, this is kind of treat it like a graph, pretend it's a graph. So a lot of students would look at this and say, oh yeah, derivative with respect to x. I mean, df dx. That's how we talk about derivatives in single variable. There's that partial symbol. That's weird. But anyway, it looks like a regular derivative with respect to x, and derivatives are slopes. A lot of students would say, oh, well, then it's the slope of that tangent line to the, well, I see a curve there at that point, so it must be the slope of that line. This is dramatically wrong. Absolutely wrong. It's not even close. Completely wrong. Again, the error, we're trying to apply an interpretation from the calculus of graphs to a picture that's not a graph. Right? So, easy mistake to make, but big problem. Okay, so let's think it through. Let's think about this for what it is. This is a level set picture. I like to think of this in terms of what do they got? Topographical maps, right? And contour lines, and hiking on mountains and stuff like that. And with that point of view in mind, I kind of messed up that last one. But here's some contour lines, and think of that as representing the side of the mountain that I'm on. And how would I feel if I were asked from this point to just start going that way, right, in the x direction? How steep is that, would I think? And notice you're kind of not quite exactly, but it's almost like you're cutting straight perpendicularly through the contour lines. That's about as uphill as you can get, almost, not quite, but pretty close to straight uphill. So that looks like a hard hike to me. I don't want to do that. I think that looks steep. In other words, that as I go in this x direction, the slope of the graph, the partial derivative is the slope of the graph. The slope of the graph that I would infer from these level sets is large. So I think that partial derivative is large. Is that cool? Now, it's not precise, right? I don't have any sense of scale here. How much vertical height is there between those contour lines? Not indicated. How much horizontal distance as I hike along? There's no legend here. I got no sense of scale. But that looks like a relatively steep thing. So I'm saying this partial derivative is relatively large. And now by contrast, if I were to go this way instead, well, I'm still going to make it up those same contour lines, but notice it takes me a lot more distance, right? So it takes me this far to go up two contour lines, as opposed to only this far to go up those same two contour lines if I were going in the x direction. So much more horizontal distance over which to gain the same altitude. So you might say, then bigger denominator, something like that. But the nice punchline then is, I think that looks like a relatively small partial derivative. Does that make sense? Again, how big are these numbers? I don't really know, but I think the x partial is larger than the y partial. Yeah. Yeah, so the idea of this is I'm imagining I'm on a hike, and these are the contour lines, and each time I go up to the next contour line, I gain, let's say, 100 feet of altitude, right? So if I'm going in the y direction, I gain that 100 feet of altitude over quite a bit of horizontal distance, right? Whereas if I were going in the x direction, I gain the same 200 feet over a very short distance. And so that looks like a steeper hike, and this looks like a shallower, gentler hike. Does that make sense? Yeah. All right. Okay. So, yeah, different interpretations geometrically in different pictures, and again, you have to kind of partition these ideas in your mind, make sure you remember which ideas are part of the calculus of graphs, which ideas are part of the calculus of level sets, etc. Okay, on to linear approximations. This is going to be our first, it's kind of an application of, so we're going to use partial derivatives to help us develop more math. It's not a physical application, but this is a mathematical development. Okay, so linear approximations, and y'all remember linear approximations from single variable calculus. Hope everybody remembers that formula right there. That is the linear approximation for a differentiable single variable function, right? Single variable, real valued, right? Good old Calc 1 kind of function. Okay, real quick observation, and I don't want to kill time on this, but technically this linear approximation is not linear. That's unfortunate terminology. You remember, linear transformations were object of great study back in Math 218, and one of the rules for a linear transformation is if you put in 0, you get out 0. Right? That's a rule about linear transformations, and this one doesn't do that. So this function's not linear. The reason that they call this a linear approximation, even though it's not technically a linear function, is because there is a closely related component of it that actually is linear, and we'll get to that in a little while. Anyway, that's just terminology, and don't worry about it. Okay, next little disclaimer, and I'm sorry to have to, I gotta have to cover myself here. I want to start off assuming that the linear approximation actually exists, because there's a lot to say about the question of whether a linear approximation exists. And that's kind of a more sophisticated discussion, and I don't want to start off with the sophisticated discussion. I want to start off with, let's get a calculation done, let's get some formulas, let's get some wins on the board, right? And after we understand what a linear approximation looks like and then sort of the nice, friendly cases, then we'll worry about, what could go wrong, and how might what we've computed not be, what circumstances could come up that would make that actually not right. Okay, so again, for the moment, I'm going to assume that everything's nice and that the linear approximation does exist, and I don't have to deal with uglier questions. Okay, so here's what it is. Now, there's different ways you can think about this formula right here. The way I like to think about it is that this formula, notice it's a degree 1 polynomial, because there's only a single power of x, right? And in fact, this is the only degree 1 polynomial that agrees with f in terms of the value at the point A and also in terms of the derivative at the point A. There's exactly one degree 1 polynomial that agrees with f in both value and derivative. And that's the linear approximation. You could think of this as that there is exactly one degree 1 polynomial that mimics f. It's copycatting f, right, in terms of value and derivative. So this is what that polynomial is. Does that all kind of look familiar? I hope familiar, or at least believable. That's satisfying. Okay. So this is the model that I'm going to choose when we write down the linear approximation for a multivariable function. I'm going to be basically ripping off this point of view, and here it is. Whoops, here it is. The multivariable analog of that single variable formula is this thing right here. Notice this is now for the multivariable case, right? Several input variables. So this is a multivariable function. Real quick side note, notice that we are, however, still only looking at real valued functions. We'll worry about vector valued functions in a minute. But for the moment, real valued only. So I claim that this is the analogous thing. Here's what I mean by the analogous thing. This function, I claim, mimics the function f in value and in the derivatives, by which I mean in this case all of the partial derivatives. And of course, look, we've got a bunch, right? We've got n different variables, and that means we've got n different partial derivatives that would have to agree with f. And I'm claiming that this function works for all of them. Okay. All right, so let me prove that for you. easy calculations. Of course, let's see here. The first one's a kind of a layup. We're going to take A and plug it in for X to compute L of A. But of course, if we plug in X equals A, then that goes away and that goes away, which means all of these terms just go away. And sure enough, we get F of A as desired. So again, that's an easy one. Nice little layup. Now where it gets a little delicate, I claim that the x1 partial of L is the same as the x1 partial of F at the point A. And real quick, a notational thing, and you might not have seen this before, but this is just notation. This business right here, where you put a vertical line and then as a subscript you put a point, that vertical line is just a way of saying, we're going to take this function, this partial derivative function, it's a function, this is a function of x, y, and z, x1 through xn. And the vertical line says, but I want to plug in a value, and A is the value that I want to plug in. So it'd be the same as if I put the A in parentheses right next to it. It's just that sometimes, especially when what follows is also in parentheses, it looks like it could be like we're multiplying the one thing in parentheses by the other thing in parentheses, and I just think it looks weird. So anyway, this is just an alternative notation. If you prefer to use parentheses, it's perfectly fine. Okay, so how are we going to confirm this? We got to be really. Oh yeah, question.
So we are multiplying by the x1 minus a1.
Yes, that's right. So what we've got here is this is the partial derivative evaluated at the point A, and yes, as you say, we're multiplying that by this thing called x1 minus a1. Yep. Okay, so let's be really careful about what the function L is. There's actually a bunch of constants in this function L. So, for example, f of A, that's a constant. A is a constant, so f of A is a constant. There's no x's in there. Right? Likewise, A1 through AN, those are all constants. And here's the thing, so are these coefficients out here. These partials, keep in mind, the partial of f with respect to xn, yeah, that's a function of a bunch of different variables, but I'm plugging in the value a. And after I've plugged in that value a, it's just a number, because it doesn't depend on how this x changes. As those x's change, I'm still plugging in the same a in here, so that's a constant. Okay. All right. So with all that noted, let's now take the partial with respect to x1. And here's the thing. When you take the partial with respect to x1, you hold all the other variables constant. That means, so for example, this xn over here, for the purposes of my taking a partial derivative, it's constant now also. And ditto for all these other terms over here. Right, there's an x2 term, an x3 term, etc. All those x's constant as I take the x1 partial. So all of this inside the big gray box here, this is all nothing but constants. And when I'm about to take the x1 derivative, and that's all just going to, of course, have derivative 0. It just goes away. The only thing that doesn't go away, notice there is an actual x1 there. And so when I'm taking the partial derivative, this one term right there, that's the only thing that has an actual remaining variable in it. And it's a constant times x1. And when you take the derivative of a constant times x1, the derivative is that constant. So, as desired. Everybody see how that works? Okay. So, now, another little mathematical weightlifting healthy exercise. I've showed you why this partial does what it's supposed to. Confirm likewise for the others. And so, for example, show that it works for the last one, for example. They're all kind of analogous, but if this is, again, a good little practice problem. Everything's going to be a little bit different. We're holding something different constant. We're a different variable is remaining a variable. It's a slightly different argument, but it's very analogous. And make sure that you can produce that argument. Again, clean sheet of paper. Don't just copy exactly. But it's very, very similar argument. Okay, how we doing? Alrighty. And let's see here. I guess we can fit all this on the page here. I want to look now at, let's see here, all of this stuff. All those terms there. And there is a structure apparent that is really useful to notice. And that is, this looks like the structure of a dot product. I have a bunch of terms. Each term has two factors, just like a dot product. Right? So, furthermore, not only does this structurally look like a dot product, but one of the, if you will, pieces of that dot product is just x minus a. I mean, we're doing a linear approximation at the point A. We're evaluating that linear approximation at the point x. You look at the vector x minus a and find its various coordinates. These are they. It's x1 minus a1 is the first coordinate, x2 minus a2, etc., xn minus an. So these green factors in here come from literally the vector x minus a. Now, dot products are meaningful and natural, and we know geometric information about dot products, so it's pretty eyebrow raising to notice that structurally this is a dot product. It is further eyebrow raising that one of the vectors is not just some random thing. It's this other natural object that's clearly in play in this process. So this is heavily suggestive that all the remaining factors, the other thing in the dot product, is also something that we should try to learn things about. It's probably natural also, right? Yet to be determined exactly what it is and why is it natural. But I'm going to give this thing a name. I'm going to call it the gradient. We're going to use this notation to represent it. Here's the general formula written in terms of a generic function g. This other factor is that thing. This thing called the gradient, which, by the way, again, it's just a notational convenience, right? I'm just choosing to define that as this. But look how convenient this is. Now all these terms here, there's a bunch of terms, dot, 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 and all that. Just a dot product. So this is a much better way to write this expression. I started with it written fully out so that we could see more explicitly what we're doing as we're taking the various partials and stuff. But day in and day out in practice, I would never write all that down. It's too clunky. Much more elegant to write it by this formula down here. Much better form. Okay. Alrighty. All right. Let's see an example. Let's take a linear approximation of that function at that point. Oh, yes, question.
How would you define the gradient in words?
I'd say let me go back up to here where I can point. The gradient, this is the notation, the gradient of a function is the vector of all of the partial derivatives of that function. Yeah. Is that cool? Yeah. Yes.
The definition of LMX.
Yep.
They're being added.
Yep.
Part of them are added.
Yep. Well, it's they're being added. They're being multiplied. So it's this times that, and then plus blah blah blah, and then this times that. So I'm not literally adding the partial derivatives. They're getting multiplied by these other things first, and then added.
Okay.
So which is what a dot product is. Yeah.
So where? Oh, that's a multiplication.
Is that cool then?
Yeah, so the delta. What's that on triangle?
It's we just call it the gradient symbol, or del. It's sometimes called del, but it's anyway. Yeah.
So the gradient of f of a is being dotted with x.
Yes, that's exactly right. Gradient of f evaluated at the point A, is being dotted with the vector x minus a, just like you said. Yep. All right, let me just, go ahead. Yes.
Is there a difference between the gradient and the Jacobian?
Yes. So the word gradient applies only if you are talking about a real valued function. So the gradient is a vector and it's real valued only functions. The Jacobian, which we haven't gotten to yet, by the way, but just it sounds like you've heard of Jacobian before, is a more general term, and it allows for vector valued functions, and also it's fundamentally a different structure. A gradient is a vector. A Jacobian is a matrix, and there are some close connections between them, and we'll talk about that next time. But yeah, they are nevertheless structurally different things. Yeah. Okay, so we're out of time. We'll pick up pretty much here next time. That'd be a good sort of like rewind for next time to start with this example. See y'all later. Have a good one.